Hey everyone! It looks like our collection of shader-generated tunnels has grown once again. This time, as you can see, it's an interesting effect created purely with points, which we can further adjust as needed. So let's get to programming it. Just as a reminder, I'm working in Godot Editor version 4.5, but everything I'll show today should work with earlier versions of Godot 4 as well. So I'll create a new scene, add a color rect to it, and assign a new shader material, just the standard procedure. So I'm right-clicking the Scenes folder, create a new scene, user interface, let's call it Point Tunnel. Okay. Right-click the root node, add child node, color rect. Color rect. Okay. Now I'll set the black color as the background and change the layout to the full HD resolution, 1920 by 1080. Okay. And scrolling down to the material section where I create a new shader material, click it, create a new shader, and it's called point tunnel.gd shader of the type shader and the mode canvas item. Everything is correct. Let's just change the folder to shaders and create, and click again to open it in the shader editor. Okay, let's expand this panel a little bit. Very well, and once again, we'll only need the fragment function, so we can delete everything else that Godot generated for us with the template, deleting vertex and deleting the commented out light. Great. So, as we saw at the beginning of the video, this will be a symmetrical effect created using a large number of points arranged in circles. For that reason, we'll move the coordinate origin to the center and adjust the aspect ratio so that the circles are true circles, not ellipses. So let's write the corresponding code. First, we need the uniform parameter defining the resolution. Uniform vec2 resolution. And the default value would be our full HD resolution, 1920 by 1080. Okay. And now in the fragment function. So let's do the usual stuff. Vec2 UV is UV minus 0.5, which is moving the coordinates origin to the center. Now the aspect ratio recalculation, uv.x is multiplied by resolution x divided by the resolution y. And finally, let's prepare the color accumulator, the variable which will be used to collect all the dots that will form the final effect. So vec3 color, RGB color, 3 components, and it starts at vec3 0, the black color. And finally, we will display that in the internal color variable, which is a vector 4, so our color, and 1 for the alpha channel. Okay. For the next part of the code, we'll need some new uniform parameters. Let's start with the color of the final effect, which will be again a vector 3, because the color will be in the RGB format. So uniform vec3 point color, and with a hint source color, which, as you probably know, means that the inspector will display the color picker 0, 1, 0, which means we will get a shade of green. Okay. Next, we'll need the size of the individual points. Let's create the points as very small circles, so this parameter will determine their radius. And since it would be a tiny value that would be difficult to adjust with a slider in the inspector, we'll later divide it by the resolution along the y-axis. So let's add this line, uniform float point size with a hint range and the default value 1. And it starts from point 1, goes to 10, for instance, with the step point 01. As we saw at the beginning of the video, the effect consists of a large number of circular layers, so we'll define their count. Uniform float layers with another hint range, and let's start with 50 layers. And it goes from 1 to, for example, 100, and the step is, of course, 1. We don't want any fractional layers. And finally, we'll want to specify the number of points per circle. Uniform float layer points with a hint range, and let's start with 100 points per circle. And it should go from, for example, 10 to 200. And the step again is 1. Okay, so let's get back to the fragment function, where we'll continue with the calculations. As I mentioned a moment ago, we'll calculate the size of the points from the point size parameter, dividing it by the resolution along the y-axis to achieve a consistent effect regardless of the size of the element this shader is applied to, this color act. So let's add it before the final color. Float size is point size divided by resolution.y. Next comes the calculation of the individual layers. So we'll need a loop in which we'll determine the depth and radius of the current layer. By depth in this context, I mean the z coordinate, assuming we consider the tunnel as a 3D object. I'll first demonstrate how to create a single layer without the loop, and then we'll add the rest. So I'll start with a constant depth and derive the layer's radius from it. Okay, so float depth is, as I said, constant 1, and let's define the radius. Float radius is 0.2 divided by the power function of depth times 0.8 plus 0.4 and to the power of 2. The constants I used in this line give the resulting tunnel a nice tunnel-like shape. If you like, you can later turn them into uniform parameters and experiment with different values and different shapes of the tunnel. Now, we'll need a function to draw a single dot. As you may remember from previous tutorials, we use this simple formula for a circle. So it's length uv minus r, which is the radius. In our case, we'll want to move the center of the dot to the distance of the current layer's radius, and radius of the dot itself will be our size variable, this one. So let's add this line. Okay, float dist for distance is length, the formula for the circle, and uv minus vector 2 radius and 0, which is simply moving the center on the x-axis to the right. Yeah, definitely. And we want to subtract the radius of this small dot, which is the size variable. Finally, we need to calculate the resulting color of the pixel and add it to our accumulator, the color variable. We cannot just add them together, because that would fill the entire screen eventually. Instead, let's use the mix function, which is a linear interpolation, and with the white value obtained from a smooth step function to create dots with soft blurred edges, like this. Color is mix of our point color and the color accumulator. And as I said, the weight should be smooth step from 0 to our size and the no depth dist, of course, and dist as the weight factor. Great. And we can already see a single dot appearing. Let's just zoom in a little bit. But to form a circle of such dots, we need to repeat the drawing around the circle's circumference. To achieve that, we'll use a conversion to polar coordinates, repeating the angle using the mod function, and then convert back to Cartesian coordinates. Since this calculation takes several lines, I'll separate it into its own function right here. Vec2, let's call it split circle, with parameters vec2, UV coordinates, and float angle to define the number of splits. So, as I said, float radius is length UV. I'm converting it to polar coordinates using the well-known formulas. Float theta, the angle is, and I said modulo, to repeat that along the circle, a tan of UVX, UVY, and we are dividing by the angle value. And finally, let's convert back to the Cartesian coordinates. So return vector 2, and now cosine of theta, sine of theta, and we need to multiply that by the radius value. That's it. Next, we need to know the angle between the individual dots, which we can calculate by dividing the full circle by the number of points in one layer. And since this value is constant, let's place it outside the upcoming loop right after definition of the size variable, which is right here. So let's do it. Float angle is tau twice pi, which means the angle of the full circle divided by layer points. Okay, and we'll calculate the new coordinates using the split circle function. The result will be used to compute the dist value. So let's make it just before the dist. This will be inside the circle we are about to write. Vec2 SUV, like split UV, is split circle with parameters UV and angle. Okay, and finally, let's replace UV in this line with SUV. Wait for it. Okay, let's zoom out and we can see the full circle. But again, we might have noticed that when we zoom in, the dots are cut off halfway, which doesn't look very nice. Luckily, we can easily fix that in the split circle function by subtracting the half of the angle value from theta. So minus angle divided by 2. Wait, and there we go. Now everything is fine, and we can verify that the effect responds to changes in the point size and layer points parameters. So let's go to the inspector, expand shader parameters, and now point size increasing, decreasing, and layer points more or less. Everything works perfectly. Okay, so that's one layer. Now we'll add a loop to display them all. At the same time, we'll adjust the depth value so that it changes for each layer. Okay, so I scroll down back to the fragment function, and now we need to place the loop right here before the depth definition. For float I from 1, I to layers number, and I plus plus, and let's put all of that inside the loop, and let's fix the indentation right here. Okay, you may ask why I start from 1 this time and not 0. The reason is that it will give us the better shape of the tunnel, because we won't be starting exactly at the 0 position. But of course, you can change it later and see the difference. Anyway, what we need to do now is to change the depth, because right now all layers are displayed at the same one. So minus I divided by layers. Yeah, this one. Okay, let's take a look. I think we can just show more of that. So the future tunnel is starting to take shape. It would definitely look better, though, if the more distant layers faded into darkness, giving the effect more depth. We can easily achieve that by multiplying point color by a value based on the current depth in the final mix function right here. So point color would be multiplied by 1 minus depth value. Perfect. And to see it better, let's temporarily increase point size to, for example, 3. Yeah, something like that. Cool. It's time to bring our tunnel to life. For that, we need a parameter to define the speed. So I scroll up to the uniform parameters section and add it uniform float speed with int range and the initial value 1. And the speed goes from 0 to, let's say, 10 with the step point 0, 1. And let's go down to the fragment function and add a new variable time, which will be based on this parameter. And since the resulting speed would be too high, I'll multiply that by 0.1. So let's add it, for example, here. Float time is time times speed times 0.1. Okay, next we need to use this value to change the depth of each layer. We know we cannot use it directly because time value keeps increasing indefinitely. So we'll use a periodic repetition of the layers and implement the movement using the mod function like this. Let's find a depth definition and improve it here. Depth would be decreased by modulo of time and 1 divided by layers. Wait for it. Okay, that doesn't look bad, but something is missing. At the beginning of the video, we saw a flight through a curved tunnel, which definitely looked even better. We can achieve that, this kind of movement, using trigonometric functions to shift the position of individual layers along the x and y axis. So let's start by writing this function. Okay, let's just stop it for the time being and write a function right after the split circle. Vec2, let's call it curve path, for example, with the parameter float depth, because it should be different for each layer to affect all layers of the tunnel differently. And we'll simply return vector2 with these values. 0.2 times cosine depth times 3 and 0.3 times sine of depth times 2. Again, a result of my previous experiments. Okay, and now we'll add a basic shift which will serve as the starting point for the offset of the individual layers. So right before the cycle starts, let's do this. Vec2 shift is the result of our curve path function with the time parameter. Okay, and finally the offset of the current layer, by which we'll then shift the UV coordinates of the points around the layer's circle. So just before SUV definition, let's do this. Vec2 offset is again curve path, and this time it's time plus depth and minus our shift vector. Okay, and we need to use it here, so it would be UV plus offset. Okay, and it's curved, and let's start it again. Now it's twisting nicely. If you want more complex movement curves, experiment with adding additional trigonometric functions to curve path function, this one, or use different amplitudes and frequencies. So basically we are done, except for one small detail. At higher speeds, let's do it. At higher speeds, the layers start to visually blend together, which can be improved by changing the brightness of every other layer. We can easily achieve this, for example, with this kind of calculation. So stopping and scrolling down to the fragment function, and just before the color accumulator, let's do this. Vec3, let's call it C, so it's pretty short, would be point color multiplied by, and this formula, which will just ensure the brightness changing for every even or every odd layer. Mod I and 2, so it switches between 0 and 1, times 0.3 and add it to 0.7. So it would be either 0.7 or 1. And finally, we can change this point color to C. And now we should see that. I hope it is visible on YouTube as well. And if we start it again, we can see that it's better, but the colors are jumping between layers. This happens because the repetition period is set to 1 divided by layers right here. Whereas now we'll need multiples of 2. So let's change it from 1 to 2. Wait for it. And now it's smooth. Nothing is blinking anymore. And if we increase the speed, it should definitely look better than before. Okay, and now we are officially done. And as usual, all that's left is to play around with the parameter settings to demonstrate different variations of the effect. So, for instance, we can change the color to something bluish or white or anything else. We can change the point size, increasing, decreasing. Let's change the number of layers. Now we have 100 layers. Now we have only 11. Everything is possible. Layer points, more points, less points, and the speed, we've already been playing with that. Let's revert to the original settings. And yes, point size a little further. Okay, and that's everything. Thank you very much for watching. I think this effect can be quite useful. For example, if you're working on a space game, you could use it to simulate a simple flight through a wormhole that takes you to the next level or a distant part of the map. Furthermore, we could control the functions for changing the flight direction via GDScript, adapting the shape of the tunnel to the current situation in the game. If you think of other ways to use it, I'd love to read your ideas in the comments or on our Discord. And as always, I'll add this shader to the Godot shader pack, so it will be available to those who want to work directly with the finished code. Anyway, take care, good luck with your projects, and I'll see you in the next video.